All right, guys. In this session, I'm gonna solve assignment one, and what I'll do is I'm gonna solve it in Matlab. But if it needs to be, I will do some on a paper, maybe problem 3, for example, where we'll draw the DH frames. Okay, let's start by working on problem 1. And what we have to do here is we have to find the homogeneous transformation between a frame 0 and a frame 3. So basically that is H03, and to get H03 we need to get H01, H12, and then H23, and then multiply all of that together. Second thing is find the rotation matrix from frame 3 to frame 0. So that is H30, which is the inverse of H03, and we're gonna pick up the first 3 by 3 column from that rotation, from that homogeneous transformation. Third is if point P is expressed in frame 0 as 0, 0.5 minus 1, we need to find a coordinate from P as viewed from frame 2. So we can do that in Matlab very easily. And find the coordinate of point P as viewed from frame 3. So we can view this point as viewed from frame 0. We can view it from all the frames. It's not a problem. Last thing is we need to find the coordinate of unit vector x1 in frame 3. Again, so get the inverse of H03 and the first row, the first column of it. Right? If you take the first 3 entries of that column, then that will be x1, right? Okay, let's go at it. So what I have here is that I have this file basically, and then I'm gonna save this file in the same folder where I have all these homogeneous transformations which I saved, and save this again. And let's begin by doing that. So when you are working in Matlab, the first line that you have to do is usually your name. Show that this is your code, and this is a solution to assignment 1. Assignment number 1. And so basically what we need to do is we need to find H01. We need to find okay, let's write it like that. And then we need to find H12 and then H23, right? And then ultimately we know H03 is going to be equal to what? H01 multiplied by H12 multiplied by H23, right? So now we have that, but let's actually, how do we, what is H01? So there are a few ways for doing that. One way would be to find it using the DH functions or DH transformations. And here basically we would need to know basically, the geometric lenses on here. And the other thing that we could do is we could do the sequence of transformations that we used, right? So we know H01, for example, is, you need to rotate, for example, the first frame by Z0 by theta 1. And then you need to do that sequence basically. And this is the method that I will use to actually solve this assignment. So what I will do is I'm gonna define my thetas as variables. So I have sims theta 1 to 3. And then regarding the geometric parameters, so the distance from, this one, usually the distance between the axes is given to you as D, right? And the distance between the Z is given to you by L, right? So I have L2 and then L3, right? Okay, cool. So what is H01? H01 is, what do I need? So I could use my DH function directly, right? Or I can use my my sequence of rotational transformation. What would be the sequence in this case? It would be, okay, so we rotate initially about Z by an angle theta 1, right? So now my x0 is pointed along x1. Then I can translate along Z by length G1. Then I'm gonna, so now basically this guy is up here and x0 is pointed along x1. So I still need to basically rotate about x, right? So Z is up, so I need to rotate about x by pi over 2. So rotate about x by how much? Pi over 2. Okay, let's check this out and just to confirm what that is. So just run that. Here we go. Okay, let's run it. Okay. So here basically we are doing some rounding for theta 1, right? And I think this is what I have done last time basically. Okay, that's fine. That works. So the situation in my Matlab basically, if I do rotation, if I try to round like pi, for example, the two figures, for some reason this function is not working. So what I did is I have another function. If I do round pi by 2, it works. But if this is a symbolic variable, it doesn't work. So probably check your MATLAB if you actually have the round function. If not, you can have the same one as mine, but still basically this is all good here. This is simply basically rounding of this function. So essentially you can think of this entity as simply cosine of theta 1, right? Okay, so this is my H01. Let's look into H12. What is H12? Okay, H12 is coming back to the assignment. So H12 is simply you rotate about Z by theta 2 and then you translate, right? So you rotate about Z by theta 2 and then you translate along what? Along X, right? Along X by L2. And similarly, H23 is equal to rotation about Z by how much? By theta 3 and then you translate about X by L3, right? Uh, so let's do this. So H03 is nothing but H01 multiplied by H12 by H23. So if I run that, okay, I'm good. So if I actually try to see what that is, so it will actually execute that. Okay, so this is my rotational transformation. If we actually put some values into theta 1, 2, and 3, so if I put theta 1 to be equal to, okay, so theta 1 is equal to 0, theta 2 equal to 0, and then theta 3 equal to 0. So let's run that. And if you do this, you see that basically this is my homogeneous transformation, right? Which makes sense, right? So the coordinate of the end effector, right? If you are at 0, 0, right? If you are at 0, 0, basically, right? So if this angle is 0, so x1 is pointing along x0, and this guy is going to be d2 plus d3, right? So this is the x-axis, right? Or I'm sorry, L2 plus L3, right? Okay, L2 plus L3, right? My y is going to be 0, and my d1 is going to be d1. If I now, let's actually, so we forgot something. So every time when you write your script, basically you have to clear the variables, right? So we're always cleaning these up. Okay. So sometimes when I'm running the script, basically I have some output, so I need to suppress the output on some of these functions. Right? If you call a function basically and then its output is not suppressed, it will actually show up. So it's always a good idea to hide all these guys, and let's run it. Okay, so this is what we have. If theta 1 was, let's say, pi over 4, you will see that you will probably have something over here, right? So, yep. Okay, so the x is actually equal to the y. And when it's doing that, basically, if you evaluate that, it will actually evaluate the output as well. So I can do H03 is equal to evaluate of H03. So just to actually call the actual, let's do that. Evaluate function maybe. Okay, not evaluate. Okay, well, this is the output is remaining like that. There has to be a way to actually to view that numerically, maybe because we still actually have some symbolic variables on here. We'll probably have to put some values for d1. Let's put d1 equal to 1, L2 equal to 1, and L3 equal to 1. We didn't change that. Okay, let's do it like that now. Okay, so there you go. So if you are at 45 degree, basically your x and your y basically are going to be equal. So this is how you can. So here, what we have basically is we are starting by doing this symbolically, and then we're converting into numbers, right? So here you simply define these as numbers, and then there you go. It's all good. Okay. So this is the first part of this problem. Let's look into the second part of this problem. Find the rotation matrix from frame 3 to frame 0. So how do I find that? So H30 is equal to what? Is equal to transpose of H03. Is that true? No, that's not true. Basically, it actually has to be the inverse. So usually we can use the pseudo inverse, which is a numerical way of doing the inverse. So if I run that, basically, I'm actually finding that pseudo inverse. All right. But let us actually, what is it? Okay, if point, so I'm gonna use this. This is my geometry of the robot. If a point P is expressed in frame 0 as 0, 0.5 and -1, how can I find the coordinate of point P as viewed from frame 2? Okay, so let's write P is given to you as what? 0, right? 0.5 -1. Okay, and remember we always add 0 at the end of it. Okay, so okay, this has to be a semicolon, um, and okay, so if we are only doing a rotational transformation, then this would be 0. But if you are doing actually, if you're looking at the actual point, then the last one would have to be basically 1, right? Okay, so this is P as viewed in frame 0. I need to be able to view this in frame 2. Okay, so how do I do that? So I know, right? I know if P was expressed in frame 0. Okay, let's actually call that P0 like that. P0. Okay, P0 like that. All right. So I know P0 is actually equal to what? H02, right? Times P2. Here, P2 basically as viewed in frame 2, right? If I want to view P2, right? So this code here is not valid, obviously. This is not a code. This is just to show you what that is. So if I want to actually find P2, I'm going to do the inverse of this guy, right? P pin of H02, and you're going to multiply this guy by P0, right? If you do that, basically now you actually calculate the inverse, or you calculate the coordinate of this point in frame 2, right? Because I'm doing the inverse of it. Okay, well, we have an error. Let's see what the error is. What is it? Okay, P inverse. Okay, we didn't define H02, right? Let's define H02. We went directly up to H03, so we need to know H0, sorry. H01 times H12. Okay, there we go. So let's do that. Okay, so here you go, right? So depending on these dimensions that I have here, right, these variables, if obviously if I change that, it will all change exactly. You know what I mean? So I'm just gonna keep it like that. So this is your point P2, and the last part is how do I find from frame 3? And that's it, right? Then P3 is equal to P inverse of H03 multiplied by P0, okay? And that is the same point as in frame 3, okay? Exactly here, it's like you are sitting in that frame and how you are viewing the point, which is already here. Now we need to find the coordinate of unit vector x1 in frame 3. How do you calculate that? Basically, we have already H03, right? So all I do is basically just type H03. What is x1? X1 is actually equal to H03, right? You take the first 3 components, right? So 1, 2, 3, right? So it is the first column, right? And you take the first 3 entries of the first column. Okay, guys, so that is it for the first problem. Now, if let's go into the second problem. What we have here is that consider the following manipulative system and external frame attached to the environment. Point P is expressed in frame 3 as 0.5, 0, and then 1. Okay, we need to find the Hunch transformation between the base frame and then frame 3. And that is the base frame, and that is frame 3. The best way here to do is we just write the transformations, right? Based on the sequences that we have. So what I'll do is, let me actually come here and then stop here. And I want to comment this part. And I'm going to call this guy problem 1. Problem 1 solution. And let me actually comment this whole thing one more time so you guys will have it. Control R. Okay. Problem 2 here. Okay, regarding, let me actually do one thing here. Just do one comment. And here I want to do that. Okay, so now we can separate them. All right. So this is the first problem. So this is the first problem now, problem 2. Let's actually begin by obtaining the homogeneous transformation between all these frames, right? So what is H01? H01 is what we're doing here between frame 0 and frame 1. So we're translating along y by 1. Then we're going up, right? We're going up by 1. We're translating along z by 1, right? So now we're here. So yep, we're good. Frame 0 and frame 1. So this guy is at the center. Y is in the same direction as y. We're good here. Let's do h1, 2. And what is that? So we're moving by how much? So the table by half the table, right? So we're translating along y by 1 over 2. Then what we're doing here, then we're coming back by x and we're translating by x by minus 0.5, right? Uh, okay, let's actually just keep it numeric. So translate about y by 0.5, then we're translating about x by minus 0.5, so we're good. Last thing is, what is the relationship between h2 3 is we're translating along z by how much? By 2. So this guy is up, but now z is opposing, right? And what do we have to do here? We have to make some rotations, right? So we're gonna rotate about z by pi over 2. So if I rotate about z by pi over 2, okay, so now x is here. So this is what you should do usually. You should just try to put one vector in the same direction as another vector and then use that to orient the rest. So this is what I'm doing. I'm rotating about z here, which was up by pi over 2. So now x is pointing to this x3. Now you rotate about x3 by how much? Now you rotate about x by pi, right? By pi. So z was up, so now z will be all the way down. And then if x is if two vectors are pointing in the same direction as the mating vectors, then we're good. Okay, so so we run that. Let's see, 500 frame 3. So we need h03, which is equal to h01 times h12 times h23. Here we go. Let's run that. So there you go. That is your solution. And the other thing is that we need to find the coordinate of point P. Where is point P here? Okay, so point P is expressed in frame 3, right? Okay. So point P is expressed in frame 3. So I can say that P0, right? P0 is equal to H03, right? Times P3, right? So P3 in frame 3, you have to multiply it by H03 to find that. Is that true or no? Yep, okay. So that is in frame 0. If you want to find that in frame 1, how do you find that in frame 1? So it could be H13, right? Times P3, okay? But what is H13? H13 is equal to what? H12 times H23. Okay, so now basically found P1, right? So P1 is equal to H13 times P3. If you want to find it in frame 2, is equal to H23 times P3. Okay, so we're good here. Very straightforward, very easy problem. Very easy problem, except we have some error. P3 is not defined. Up is not defined. So P3 is equal to how much? Remember, this is a column, right? And 0.501. 0.501. And then don't forget the one at the end. But if you don't include the one at the end, basically, you will simply, it's like you take the vector, right? P3, which is from the origin of frame 3 to the point P3, and then you try to, kind of transform the coordinate of that vector. Okay, let's run that. Okay, so these are the points, right? So this is P1, and then this is P2. Coordinate of that point in frame 1, and then this is the coordinate of that point in frame 2. Okay, guys, so this is the second problem. Now let's solve problem 3. What do we have here? We have to label the H frames on this robot and run the Hunch transformation between the base frame and then the vector. Okay, so we have to put the H frames on this robot. Okay, so we'll start by putting the Z vectors. So this is my Z0, and this guy is my Z1, right? Okay, let's actually write it. So this is my Z0 is here. This is my Z1, right? Okay, let's move that a little bit. So this is my Z0, this is my Z1. Now we said the second thing is you have to put my x0, my x's, right? So I want to put my x0 like this, right? This is my x0. What is my x1? X1 has to be perpendicular to z1. It also has to cross z0, right? So this is my x1 has to be like that. Okay. This is my x0, and this is my x1. Okay. Let's move this a bit. All right. How about, so, how many degrees of freedom here we have? Two links, right? So we have to have two frames. Frame one is connected to link one. So x1, z1 basically will rotate, will this link. We still need to have frame here that we didn't include. So I need to put that too. So this is my z2, and then that is my x2. Okay, this is my z2, and then this guy here is my x2. Okay, we're good. Okay. Okay, so this is your DH frames. Find the velocity. Under the dimension transformation between the base frame and the end effector. Okay, so we have to write the DH here, right? Okay. All right. So let me clear the graph. So we got that, right? So I'll clear all my drawings. Okay, so we have to get our DH transformation, right? Okay, so what is my DH? H01 is it's a DH function, right? We have to have this variable here, right? A. So we said what was A is a distance. Well, we should have that, but that's fine. So we said, we remember, right? So basically simply x1 was here, right? X1 was pointing like that. So there is not much to it, right? And then z1 was here. So A is, if we remember, A is a distance between what? Between the C axis, right? So this is my Z0 is like that. And then this is my Z1, right? So A is going to be the distance of this guy, right? Let's actually comment this out first. Okay, let's call it, let's make it 1. All right, so A, and then I have alpha, right? So I know Z0 was pointing outward, and then Z1 is like that. Actually do something very quickly here. And I want to actually come back, open up my video, so I can show that to you here. So this is the first joint. We have this guy coming up like that. And then we have this guy. Okay. And let's make this a little bit bigger. Okay, so we said x0 is like that. And then this is my z0. My z1 is here. And this is my x1, right? And this is my z2. And this is my x2, right? Okay, we said theta is going to be the angle between x0 and x1, right? This is my theta 1, right? And we said A is the distance between what? Between the z-axis, right? So this is my A1, okay? This is my A1, and D1 is the distance between the x-axis. So this is planar, right? So this is between x0 and x1 is 0. Now let's look into, next one is basically A here is the distance between the z-axis 0, right? The z and the z are collinear here. So we literally only have this guy, which is D2. If I were actually to look into the DH table, so I'm gonna have link 1, link I, A, alpha, D, and then theta. So A is A1. Alpha, we said alpha is what? Alpha is the angle between the z-axis, right? And that is about x1, right? That is the reason, by the way, why x1 has to be perpendicular to z1 and then also crosses z0. So what is the angle between z0 and z1? about x1, it's going to be pi over 2, right? And d is the distance between, is the offset between the x-axis, which is 0 in this case, and then theta is theta 1. All right, and then 2, what is the a distance, right? A is the distance between the x-axis, I'm sorry, z-axis is 0 in this case, right? This is between the z-axis or collinear. What is alpha? By how much you need to rotate z1 to bring it to z2 about x2 is 0, right? How about d is d2, and how about theta? X2 and then x1 have the same collinear. Okay, so if I come to MATLAB, basically I will just write that, okay? You know, oops, because that sims a1, theta 1, and then d2. I'm just assuming, I was assuming a1 to be a variable, but let's assume not to be a variable. Let's theta 1 and then d2, right? These are the variables, and then a1 let's call it to be equal to 1. Now h01 is going to be a dh, right? Okay, a1 alpha is pi over 2. What is d in this case? 0, and then theta 1. So we get the first one. h12 is equal to dh what? 0, 0, d2, and 0, right? Okay, so h02 in this case is going to be equal to what? h01 times h12. Let's run that. Okay, so I'm gonna close this up and I'm gonna run that. Okay, so this is my h0 function, right? This is my h02. So the second part of this problem is we need to actually find the velocity of point A as a function of the joint positions and velocities. Use differential chain rule, okay? So we need to find the velocity of point A, and then this is actually the second topic that we are actually going to do, which is basically differential kinematics. If you actually see here, right, this is nothing but cosine theta 1, right? Here there is just this issue in my particular MATLAB here installment. The round function is not working well, so I need to fix that. But here, if you actually see here, basically I have cosine theta 1 plus d2 sine theta 1. Okay, so I'm just gonna write that. So this is a coordinate, right? So this entry here is what? Is x of my end effector, right? So x is equal to, I'm writing that on a paper now, cosine theta 1 plus d2 sine theta 1, and then the y of my end effector is equal to what? Let me actually, I'm sorry. Okay, here we go. So x is equal to cosine theta 1 plus d2 sine theta 1, and then my y is equal to how much? Sine theta 1 minus d2 cosine theta 1, okay? All right, so now if I ask you to find the velocity, right? If I ask you to find the velocity as a function of find the velocity of point as a function of the joint position and joint velocities. So what is the joint velocities? عندنا theta 1 prime and then عندنا d2 prime, right? So the time rate of change of the variable theta 1 is basically how fast this joint is moving, and d2 prime is basically how fast this prismatic joint is telescoping, right? That is d2 prime. So if I'm trying to find the velocity of this guy, how can I find that? So x is a function of two variables, ما هيك theta 1 and d2, right? If you try to differentiate a function with two variables, so what is dx? Dx is actually equal to what? df, ما هيك df over d theta 1 multiplied by d theta 1 plus df, the partial derivative of f with respect to d2 multiplied by d2, okay? Now, obviously, I need the time rate of x, so I just divide by dt here, okay? So in reality, x prime, which is my velocity, is equal to df d theta 1, right? F is actually x, right? So dx d theta 1 multiplied by theta 1 prime. So I need to know that, right? I need to know by how fast this guy is moving and how fast d2 prime is moving to be able to actually get the velocity of that. Plus df d2 multiplied by d2 prime. Okay. All right, this is the velocity of x. So let me just do that a second here. Now we're trying to find. Now, how about the y prime velocity? The y prime velocity is in a similar manner. So I'm going to do dy d theta 1 times theta 1 prime plus dy dd2 times d2 prime. Okay, I can do this here very easily, or I can do it in Matlab. I like to do it in Matlab because I find it to be easier. So let us actually, let me actually, I can write it here. Okay, let me just do it here in the command window. I'm gonna do x is equal to um, uh, theta 1 is still a variable, right? Theta 1 is a variable, d2 is still a variable. Well, we need to know theta 1 prime, right? So I'm gonna just define it as omega 1, okay? And I'm gonna define d2 prime to be v2, okay? Okay, d2 is basically the telescoping velocity of this guy, right? Which should be provided to you in order for you to find the velocity of this point, right? Okay, so this is it. So now let's actually write what is x. X is equal to cosine theta 1 plus d2 times sine theta 1. Y is equal to sine theta 1 minus d2 times cosine theta 1. Okay, just x and then y. So if I want to find the velocity, right, v in x direction is equal to diff is a partial derivative of x with respect to what? Theta 1, right? That is this guy, right? So in MATLAB, right? So this is the x, this is diff of x with respect to theta 1 multiplied by theta 1 prime. What is theta 1 prime? We call it omega 1, okay? Plus the other one is here, right? So it's d f diff. So this guy in MATLAB is diff x, x with respect to what? With respect to d2, right? Which is already a symbolic variable, so we can do that. And we said the telescoping velocity. What did we call it? Telescoping velocity. We called it v2, right? So there you go. So this is your velocity in x direction. Okay. Now let's look into the velocity in y direction. Vy. It's diff. Go up a little bit. Okay. So it's diff y with respect to theta 1 multiplied by omega 1, right? Plus diff of y d2, right? Multiplied by v2. Okay. So this is your velocity in x, and then this is your velocity in y. Then I think you guys see that why that is true. If let's do it analytically now. If I do dx d theta 1 is going to be equal to what differentiation of cosine is minus sine theta 1, and then partial derivative. Okay, so dx theta 1 is equal to that. Dd2 is equal to how much? Or dx dd2 is equal to sine theta 1. Okay, so if I calculate now, what is my x prime? Okay, dx, oh wait, so dx d theta 1 is equal to what? Minus sine theta 1, you forget that, right? Plus d2 cosine theta 1, right? When I differentiate dx d theta 1, I still actually have this guy, right? Okay, so dx theta 1 is equal to minus sine theta 1 plus d2 cosine theta 1, which is here. And differentiating y, right? This guy is y, dy dd2, right? This is x, sorry guys, x. And then dx dd2 is equal to dx dd2 is equal to sine theta 1. Okay, so what is x prime is equal to minus sine theta 1 plus d2 cosine theta 1 multiplied by theta 1 prime plus dx2, which is sine theta 1 multiplied by d2 prime. Okay. Um, All right, one more time here, nice and clean. So x prime is equal to minus sine theta 1 multiplied by theta 1 prime, right, plus d2 cosine theta 1 multiplied by theta 1 prime plus, I'm sorry, sine theta 1 multiplied by d2 prime, right? So if you compare these, right, the first one minus sine theta 1 times theta 1 prime is here, right? This is the first guy, first term. The second term is d2 cosine theta 1, right? What is it? Okay, d2 cosine theta 1 times, okay, what is going on here? Okay, well, okay, yep. Okay, so this term is correct, right? Sine theta 1 times d2 prime, right? This is this guy. Okay, this guy is good. And what do we have here? Basically, we have minus omega 1 sine theta 1, which is this guy. So this guy is good. And then the last term basically seems to be negative, and then we got it here as positive, right? As d2 cosine theta 1. Okay, d2 cosine theta 1 is coming from here, right? And when I differentiate dx with respect to d theta 1, I'm gonna end up with d2 cosine theta 1, right? And if I actually do that, okay, so here we're differentiating the x back to theta 1. So here we go. So dx with respect to theta 1 is minus sine theta 1 plus d2 cosine theta 1. And okay, then what we have, okay, so so this is our, okay, so dx d theta is actually fine, right? I think the issue is here when we're multiplying dx d theta by theta 1 prime, right? Which is minus sine theta 1 prime plus d2. Okay, so okay, dx d2, which is sine theta 1. So this guy basically should just be a negative. No, actually, no, this is actually correct. And it looks like, okay, so this minus here actually is multiplying omega 1 by that. So minus times minus is actually positive. Okay, guys, so this is actually all good. We're good here. So this is just, the issue that I didn't see. So minus omega 1 times the 1, and then minus, and minus is positive. Okay, guys, so that is really the solution here, all right? And any questions on that, just let me know. Overall, you can see we can really use Matlab very effectively to be able to handle really complex problems in a very simple manner in robotics. Okay, guys, any questions, just email me, let me know, and I'll be very happy to help. Okay.